Till now we have discussed insertion sort, merge sort, heap sort, and now in this video we are going to be discussing about quicksort, right? So quicksort is a sorting algorithm such that its worst case time complexity is theta of n square, right? So it is not a very good time complexity for an algorithm because merge sort, as we have already seen, sorts in theta of n log n time, alright, in all the cases. So quicksort lags behind merge sort in the worst case. Why? Because its time complexity is theta of n square, right? But quicksort is very much preferred. Why? Because its average case time complexity is theta of n log n, which is much better than theta of n square, and it seldom happens that it hits the worst case, right? So on average it sorts in time theta of n log n, which is a good time complexity for a sorting algorithm, right? So it is very popular. And also quicksort is an in-place algorithm. What is an in-place algorithm is, it takes extra space, it takes constant amount of extra space, right? That is, the space complexity is theta of 1, that is, it does not require space depending on the size of the input, right? So it is a very good thing that an algorithm is in place, right? What is in place algorithm? In place algorithms are the ones that take constant amount of extra space, right? So quicksort, just like merge sort, falls in the category of divide and conquer algorithm. As we have already seen in merge sort procedure as well, divide and conquer just sorts in 3 ways, or it works in 3 steps, right? So what are the 3 steps? Divide, conquer and combine, right? So what is divide? In the divide step, what we do is, we divide the problem into a number of sub-problems, right? And then what we do, we conquer the sub-problems by solving them recursively, and then we combine the solution of these sub-problems to form the solution of the original problem, right? That is, first we divided the problem into a number of sub-problems, and then we solved these sub-problems, and then we combine the solution of these sub-problems to find the solution to the original problem, right? So that is how the divide and conquer paradigm works, right? In quicksort, in order to divide the problem into sub-problems, what we do is, we divide the array into 2 sub-arrays, right? Let us assume that the array A, which we want to sort, has indices from P to R, right? So what we do is, we divide the array A into 2 parts, from P to Q minus 1 and from Q plus 1 to R, such that all the elements from P to Q minus 1 are less than A of Q, and all the elements from Q plus 1 to R are greater than A of Q, right? What I mean to say is, if there is an array A that we have to sort from indices P to R, right? So we have to find an index Q in the array such that we have to find an index Q in the array such that from P to Q minus 1, these elements have to be less than equal to A of Q, right? All the elements in this part have to be less than equal to A of Q, and all the elements from A of Q plus 1 to R have to be such that they are greater than A of Q, right? Let us say if A of Q is 5, then this set can contain, I am just taking an example, it can contain 3, 2, 1, and this set can contain 8, 9, 7, 6, right? So we have found an index Q such that from P to Q minus 1, all these elements are less than A of Q, less than or equal to A of Q, and all these elements from Q plus 1 to R are greater than A of Q, right? So we have to partition the array into like this, right? So we have to divide the array into 2 sub-arrays, right? So that is about the divide step. And in order to conquer the algorithm, what we do, we just call the quicksort recursively in order to solve it, right, till it reaches the base condition. And combination step is not required because it is an in-place algorithm, and at the end of the quicksort, what happens is, from P to R, array A from P to R is already sorted. That is the result of this algorithm, right? So this is how quicksort works, right? So the main algorithm or main procedure involved in the quicksort is the partition procedure. Alright, so partition procedure is the main part of quicksort algorithm, right? So what it does is partition finds an index q or returns an index q such that this is less than this and all these elements are greater than this. All right, so the partition procedure makes sure that we get an array like this, right? So the main thing is partition, and we call partition procedure and quicksort recursively in order to sort the array. So first we will look at the partition procedure, how it works, and then we will jump on to the quicksort on how it makes use of the partition procedure in order to sort the array, right? So first we have to discuss about the partition procedure, right? Let us say that the array that we want to sort using quicksort is this. 2, 8, 7, 1, 3, 5, 6, 4. Alright, so this is the array that we want to sort, right? First, but we have to look at the partition procedure. So we will look at how partition procedure works on this array, right? So we will just do the dry run. 1, 2, 3. Let us say the indices are starting from 1, 5, 6, 7, 8. There are 8 elements present in the array. Let us say that the array is A. Alright, so we pass the array A. Now what are the parameters of the partition function? A, P, R. So A is this array. What is P? P is the starting index, that is P is equal to 1, right? And R is equal to ending index, that is R is equal to 8. We could have taken a smaller part of it if we had to sort just this small part, right? But we have to sort this entire part, or we have to partition the entire part. So we are taking P is equal to 1 and R is equal to 8, right? So now let us see what it says. X is equal to A of R. Also, what do we do in partition procedure is we just take an element that is called a pivot element. We can take any element. It can be a middle element or starting element or the ending element, such that we partition the array around that element. For example, if I say that in this case or in this procedure, what we have taken is we have taken the last element as the pivot element, right? So the element around which we partition the array is called as the pivot element, right? So this, let us say we have taken the last element as the pivot element. So what we do is around 4 we will partition the array, that is we will find the elements less than 4 and greater than 4, and then we will partition it into 2 halves, right? Let us see how it works. X is equal to A of R. What is R? 8. A of 8 is equal to 4, right? So X is equal to 4, right? Now I is equal to P minus 1. Now I is equal to P minus 1. What was P? 1. So I is equal to 1 minus 1, that is 0. So I points somewhere here, right? Now for J is equal to P to R minus 1. That is J is running from here to R minus 1, right? That is till this index, right? Because this is already done, or this is taken as the pivot element. So we have to examine this part of the array as to which elements are smaller than this element or which elements are greater than this. That is, we have to run the array from the starting index to the last index minus 1, because we need to find which of the elements in this array are smaller than the pivot element and greater than the pivot element, so that we are able to divide the array into 2 halves, right? Not halves, into 2 parts, right? It may not be half, it may not be divided into half. It might turn out that all the elements are just present on 1 half, right? It might happen in that way. So we cannot say that we are dividing the array into 2 halves. We can say that we are dividing the array into 2 parts. All right. So I is equal to P minus 1. J is running from P to R minus 1. All right, from 1 to 7. J is going to run from 1 to 7. Right. Now, if A of J is less than equal to X, what is J now? J is starting from here. Now, at the beginning, what is J? J is equal to P. J is equal to 1. Right. Why? Because P is equal to 1. Now J is equal to P to R minus 1. From P to R, alright, we have seen that, right? If A of J is less than equal to X, A of J, what is A of J? 2. A of 1 is equal to 2. If 2 is less than equal to X, what was X? X is equal to 4, right? X is equal to 4. Is 2 less than equal to 4? True. What it should do? I is equal to I plus 1. I should be incremented, right? I should be incremented now. And what should it do? exchange a of I with a of j. But I and j both are pointing to the same element, so when we exchange it, it will remain the same. That is, it is saying exchange 2 with 2. Nothing will happen as a result, right? So it will remain like that. Now this loop is ending. This loop is till there, right? So now j is equal to 2, right? Because we haven't reached r minus 1, that is 7. So now j is incremented to 2. J is incremented to 2. Now what we have to see, if a of j is less than equal to x, if a of j is less than equal to x, that is 8 is less than equal to 4. Is 8 less than equal to 4? No, it is false. So nothing will happen because this condition fails, so this will not be evaluated. Now again j is equal to 3, right? Now j is equal to 3. Right? If a of j is less than equal to x, is 7 less than 4? No, it is not true, right? So this condition will fail and again j will be incremented, simply incremented. Alright, so whenever this condition fails, what is happening? J is simply incrementing, nothing is done. J is simply incrementing by 1, right? Because this condition fails, right? Now j will be incremented. Now j is equal to 4, right? If a of j is less than equal to x, is 1 less than equal to x? True. Is 1 less than equal to 4? True, right? So what will happen? I is equal to I plus 1. Now I is equal to I plus 1. And exchange a of I with a of j. That is 8 and 1 have to be exchanged. Right? So now again j will be incremented. J will be here now. Alright, is 3 less than 4? If a of j is less than equal to x, is 3 less than equal to 4? True. What will happen? I is equal to I plus 1. Alright, so I is equal to I plus 1. Now I has to be incremented. And what will happen? Exchange a of I with a of j, right? So 7 and 3 will be exchanged. 7 and 3 will be exchanged. 3 will come here, 7 will go there. Alright. Now j will be incremented. Now let us stop here for a while and let us see what is happening inside this. So what is happening is, what does index I represent? I represent the maximum index till which all the elements from the beginning of the index till the index I are less than the pivot element. What is the pivot element? This one, right? That is A of R, that is x, right? So x is the pivot element, right? So from P to I, all the elements are such that they are less than equal to x, right? 2 is less than equal to 4, 1 is less than equal to 4, 3 is less than equal to 4. So what this partition function does is, while it is running the for loop or while it runs, what it does is, it divides the array into 4 parts. That is from P to I. From P to I, what happens is all the elements are less than equal to x, or all the elements are less than equal to the pivot element, right? Now from I plus 1 to j minus 1. This is j minus 1. If this is j, this is j minus 1. From I plus 1 to j minus 1, that is 8 and 7. What happens is, all these elements are greater than the pivot element, right? All these elements are greater than the pivot element, right? And from j to r minus 1, right? From j to r minus 1, these elements we have to examine. We have to examine 5, we have to examine 6. And accordingly, we have to place in one of this group or this group, right? Either we will place in this group or we will place in this group from j to r minus 1. That is the third part, right? First part is from p to I, second part is from I plus 1 to j minus 1, third part is from j to r minus 1, and the fourth part is x is equal to a of r, right? So that is how partition partition function as it runs, it divides the array into 4 parts, right? Now whenever we run through the loop, you can check it at any point of time. I will always point till the last index from P, or till the maximum element index from P, such that all the elements from P to I are less than a of x, right? Sorry, a of r, right? So that you can check along the run of the partition procedure, right? Let us examine even more. Now J is equal to J is equal to 1, 2, 3, 4, 6, 8. Yeah, J is equal to 6 now, right? So if A of J is less than equal to X, is 5 less than equal to 4? No, it is not less than equal to 4. So what happens? It just moves. Alright. So what is happening actually, when it is not able to find an element less than X, it will move 1 point forward, right? Or 1 position forward. Anyway, from I plus 1 to j minus 1, it will always be greater than x. So it will move forward. It will simply move forward. And when it finds an element less than 4 or less than the pivot element, what it does is it increments I. Why? Because the number of elements that are less than the pivot have incremented, and then it swaps the two elements. Why? Because the element that it discovered now is less than equal to x, and now it increments I and then swaps it. We will look at it in a clear way, right? So first let's understand the loop. Let's run through the loop, right? So now what happens is, now j is equal to 7. Is A of j less than equal to x? No, it is false. So nothing happens. Now j is equal to 8. So for j is equal to 8, it will break, because j has to run from p to r minus 1, right? So it just breaks here and just comes down to here. Now exchange A of I plus 1 with A of R. Why? Because from P to I, all the elements are smaller, and from I plus 1 to j minus 1, all the elements are larger than A of X, or sorry, A of R. So what it does is, what is the correct position of A of R? I plus 1, right? So what it does is, it exchanges I plus 1 with A of R, right? So it exchanges 4 with 8. Because the correct position of 4 is here, because before 4 all the elements are less than 4, and after 4 all the elements are greater than 4. So what is the correct position of 4? Here itself, right? So we have inserted it here and returned I plus 1. That is, we have returned the index q that we will catch in the quick sort, right? So now have you understood this? What is happening? That is, I till index I, all from p to I, all the elements are smaller than x, and from I plus 1 to j minus 1, at any iteration of loop, what happens? All the elements are greater than A of x, right? So it happens something like this. It wants to partition the array into something like this, right? There is an element, pivot element x. Now all these elements are less than equal to x, and all these elements are greater than x, right? So what happens when it discovers an element? Let me rub this. I hope you understood this. Or I shouldn't have rubbed this, right? So what happens is, let us say, if at any point of loop, this is I, right? Is it visible? Let us say this is I, alright, and this is j. Let us say it discovers that A of j is greater than x. A of j is greater than x, so what it does is it simply moves forward, because what should be the case? From I plus 1 to j minus 1, all of it should be greater than x. So this is greater than x, so done. So it just moves forward. But if it finds an element, let us say here it finds an element that is smaller than x, right? So what it does is it increments I. So all these elements are greater than x or greater than A of R, and all these elements are smaller than equal to A of R, right? So what it does is, when it finds an element smaller than A of R, then it has to be put in this group. So what it does is it increments this one. It points here. It increments I, because now it will contain even more elements, right, which are smaller. So what it will do, it will increment I and swap just these two elements, right? So what will happen? Smaller, now again this property will hold, that is greater than less than equal to A of R. This property will again hold, right? And again when j moves here, since we put the larger element here, earlier it was smaller element, now we have put larger element there, again from I plus 1 to j minus 1, what will happen? All these elements will be greater than a of r, right? So it is maintained throughout the procedure of partition. I hope you got how the partition procedure works, right? So alright, so I hope you got the partition procedure, and we will discuss how quicksort makes use of partition procedure in the next video, in the upcoming video, right? So this is it for this video. I hope you like this. If you do, then please don't forget to press the like button down below, subscribe to my channel for more such videos, and press the bell icon so that you get notified every time I upload a new video. I'll see you in my next one. Bye.